Okay, I can see. And the title is Trace Identities for Special Jordan Algebras, and he's from University of Campinas. Thanks.
Hello. Uh, Thank you so much for inviting me for this talk. Okay, I'm a little nervous, but I will try to speak English in this walk, in this talk. Okay. Okay. Uh, okay. Uh, the title of my talk is Trace Identity for Special Jordan Algebra. Okay. This talk it's very important for me because I spent many years for this subject. Okay. Uh, to kick off my presentation, I will talk a little about the story of this problem. Okay, in 17th, Hasmislov and Proches uh, proved that this problem, okay, in characteristic zero, all trace identity for matrices are consequence of the Cayley-Hamilton polynomial. This problem it's very important in PI algebra and motivate many problems in this area. So it's natural to study the trace identity in other variety of algebra. Around 1982, Shestakov in the next notebook proposed the follows problem about central simple Jordan algebra. These algebras have these algebras have affinity basis of trace identities. Another question can be this: do they satisfy the expected property? Motivated by this problem, in 1971, 1991, Vasilevsky answered this question when considered the Jordan algebra of a non-degenerate symmetric form, okay, denoted by this Bn. Recently, in 2018, Denise Koshilkov and myself obtained that algebra satisfy the expected property. Okay. Uh, for other central simple Jordan algebra, this problem open still now. Uh, the purpose of this talk is to communicate for us that it's that problem is resolved uh, over a field of characteristic zero. Okay? Uh, such problem is still open over a field of positive characteristic, and in the same work uh, have many consequences of these results. Okay, we we can, for example, as a proof that the ideal of trace identity for each one of these Jordan algebras satisfies the expected property. This talk is based on a joint work with Claudemir Fidelis at UNICAMP and Ivan Shestakov at the USP. Okay, and it is submitted at the moment. Okay, uh, moving on some preliminary. In this talk, we consider an algebra, a vector space equipped by the linear form, okay, over a field K. Algebras can be associative, commutative, or unitary. In, in a natural example of algebra is a vector space of matrices equipped by its usual product, okay. Another example comes from Jordan algebra. Uh, Here in this talk, non-associative algebras means not necessarily associative algebra. An algebra is called Jordan algebra is if it is a commutative non-associative algebra and satisfies the Jordan identity, this guy. Okay, a simple example is when take an associative algebra A and we see its vector space structure equipped by the Jordan product denoted by this. Okay, it is easy to see that this new algebra is a Jordan algebra, and the Jordan algebra of this type, as well as the sub-algebras, are called expansion, and otherwise they are expansional. Okay. Okay. Now I need a break to talk about the algebra with evolution, because evolution associative algebra play an important role in the classification of the central simple Jordan algebra. In this case, we consider A an associative algebra, and the map star from A to A is called involution on algebra A. If satisfies this guy, and this guy, okay? The pair A star is called an associative algebra with evolution. Okay. If I can draw your attention, in this definition, we need to consider the map over ground field is the identity map, okay? If it occurs, we call this evolution is of the first kind. Otherwise, it is of the second kind. Okay, I brought two examples of involution on matrix algebra. The first one is the transpose involution. It changes the column by room in square matrix, okay, of the order n. And the second one is the symplectic involution denoted by x. It's important to see that it is defined only n is even. It is defined this way, okay? It well know that these two involutions in over a algebraic closed field, it's only this involution existing. Okay. We consider the vector subspace of symmetric elements on associative algebra with evolution. I denote this set for this, okay? This guy equated with the Jordan product is a Jordan algebra, and it is a subalgebra of this algebra A+. Concretely, we can see this algebra of symmetric elements on transpose evolution, and this algebra is the same when considered the symplectic involution. Okay. As we can see, the classification of this special central simple Jordan algebra is closed by involution on associative algebra. In that moment, assume the field is algebraically closed, and the complete classification of the special central simple Jordan algebra up to isomorphism, it is given by this list, okay? Or it is a Jordan algebra of a non-degenerate symmetric linear form on a vector subspace, a vector space of dimensional greater more 2, or the the vector subspace on element symmetric in matrix on transpose involution or symplectic involution, or the last one is the matrix equipped by Jordan product. Okay, and if you raise the adjective special in this phrase, uh, we add more one Jordan algebra in this list called Albert algebra. Okay, in this talk, it's not necessary to include this algebra in this list. For this, I I will talk of this algebra another opportunity. Sorry. Okay. Now I will talking about the trace algebras. Okay. Uh, the simple example was of the trace algebra is matrix. We consider the symbol for matrix with entries in a field of characteristic 0. By Kelly-Hamilton theorem in linear algebra, every matrix is 0 of the characteristic polynomial in this way. Okay. Here, the symbol is identity matrix of the order n. Um, it's not easy, but it is usual check the characteristic polynomial can be expressed as a polynomial whose its coefficient uh, is trace of the power matrix X. Okay. For example, when consider n equal 2, the characteristic polynomial of degree 2 is this guy. Okay, so it could be nice to generate this notation for more general algebras. We take a non-associative interior algebra A, and we consider its center denoted by this, denoted by Z. Center associative and commutative center, okay? In this case, K-linear maps denoted by tau from A to its center that satisfy this guy and this guy is called tracing on algebra A, okay? The pair A and tau is called trace algebra for us. I can draw sorry. As you can see in this property, the red property, it's not necessary occur by to define the trace on any algebra, okay? But in our case, this is occur if for is I put in this property here, okay? Here, this symbol is the commutator between two elements in A. it's important to see that this is associated because in this algebra it's not necessarily associated, but when I apply the map tau, I have equals 0. I brought three examples of trace algebra here. Of course, these algebras have a relationship with matrix algebra, okay? We consider algebra A as a matrix algebra, and we consider TR the map usual of the matrix algebra. The trace is the sum of the diagonal entries of the square matrix. It's easy to see that this pair is a trace algebra. Okay, comes from this. When consider the Jordan algebra of the symmetric elements on transpose or symplectic involution, equated by this trace 2, are also examples of trace algebras, okay? Of course, there are very many other interesting and important examples of the trace algebra, but I give this example because I will work extensively with them in this talk. Okay, I need I need some notations for my talk. K here is a field of characteristic 0. The symbol is the free algebra with unitary freely generated by X. Here, TR is a formal trace over the free algebra, and the symbol is algebra generated by this set. Here, this element and this element are in free algebra, and this algebra is this algebra depends on the variety of consider If for this I call of algebra of generalized polynomial in a variety V, and their elements are called trace polynomial. Okay. As it is usual define the identities in some variety, in my case, I need this notion of the identity on trace algebras. We consider a tau a trace algebra in a variety V, okay? A trace polynomial in this GX algebra is a trace identity for the pair I tau if for substitution TR by tau we have this element equals 0 for any A1 until AN in algebra A. This definition is usual to an ideal A in this algebra is called TR ideal or T ideal with trace if for every trace polynomial in this ideal, in every polynomial in free algebra, the trace polynomial defined by this lives in ideal A, okay? An example of the identities, the trace identities, it follow from linear algebra. we consider this polynomial, okay? As well as its linearization. It's a trace identity for matrix or of the order n. Here, when n equal 1, we have this definition of this polynomial. This polynomial is called Cayley-Hamilton polynomial, and for example, when n equal 2, we have this polynomial, okay? We can prove that for induction on n. Okay, now I'll talk a little about my results, okay? The technique, it's simple, it's usual, but not easy. To begin, to start off, we want to describe the trace identity of minimal degree for each one of these algebras listed previous. Okay? Here, we consider the element in this algebra will be denoted by this way, f plus, in associative algebra of the generated polynomial with evolution. Here we denote this algebra by this, okay? In this case, we replace the usual product here by the Jordan product here, okay? And this case, F plus is a associative algebra. Is the associative element in this algebra G X cup X star. Okay. In this way, if we consider F a trace identity for Jordan algebra in this case, or this case, or this case, then when can see in generate polynomial with evolution, change the variables x by y1 until yk. Here, y1 and yk is a symmetric variables in the free algebra with evolution, of course. In this case, associative. Okay. In this case, this element is a trace identity for matrix when consider only, where it is evaluated only for elements in Jordan algebra. It's an annotation of the weak trace identity for the pair matrix Jordan algebra. Okay. Okay. In 1976, Purchase proved this result. When consider the matrix algebra over a field of characteristic 0 with the usual trace, the minimum degree of the trace identity for the matrix algebra is obtained by complete linearization of the Cayley-Hamilton polynomial of degree n. In this case, Purchase proved that any trace identity for matrix follows from the Cayley-Hamilton polynomial of degree n. Okay, of course, the degree n is the order of the n is the order of matrix. Okay. The second one, when you consider the transposing evolution on matrix algebra, we have then every trace identity for this pair, this evolution, this associative algebra with evolution is of degree more n. Okay, here don't only one element in this base, but we have the minimal degree in these trace identities. Okay, as consequence of this result, and because we have the Jordan algebra is power associative algebra, Pushnikov, Shestakov, and myself obtained this result, okay? We consider the matrix algebra over field of characteristic zero with the usual trace. The minimal trace identity for matrix algebra equated by the Jordan identity, Jordan product in this algebra is a scalar multiple of the complete linearization of the Cayley-Hamilton polynomial of degree n. Okay. In this case, we have the minimal degree of the trace identities. When considered the Jordan algebra of the symmetric elements in this involution, we have the similar result for the minimal degree of the trace identity for the Jordan algebra. Okay? In this case, we can draw your attention by this element. We can see only one generator in set X. As a consequence of this result, when consider the algebra of generalized polynomial in one generator, for example, X in the set X, the TIT with the, our trace identities of the Jordan algebra in this guy and this guy is equal this T ideal generated by the Cayley-Hamilton polynomial of degree n. This symbol is denote the ideal in this algebra, okay? The intersection between this ideal and this algebra. Okay, this is important because I'm not sure if any of you know, there is this remake, okay? This remake is usual in the theory, and I need this for my results. 2T, of course, this result, this remake for the case of the ordinary identity, but we deduce for my varieties of algebras. Okay, 2T TR ideal I and J, I equal modulo the Capet type trice polynomial of the order k plus 1. If and only if this TTR ideal is equal when considered in pre-algebra in k variables, okay? This is remake. For this is remake, we will need to notation of Capet polynomial for my case. This definition is the general, okay? But we consider polynomials in this algebra. We take f and a polynomial in this algebra, which is linear in m first variables. This polynomial, defined this way, is called Capet type trice polynomial of the order m. Okay. For this and this remake and this corollary, we have ingredient to discuss about the base of the trace identity in these algebras. Okay. Move on the next slide to present the main result of this talk. In this case, we will require a set of technical lemmas, but I brought only two these lemmas. The first one, if the Jordan algebras have dimensional equal R, then this polynomial, that polynomial is a Capelli type polynomial, price polynomial, is identity for Jordan algebra whenever this k is greater than R minus 1. Here, the symbol is that polynomial, okay? The price polynomial. Okay, this is a trace identity of the Capelli type for the Jordan algebra finite dimensional. The second lemma, it's very important for us. We say that, that every multilinear Capelli type trace identity of the order 2 for the Jordan algebra J is a consequence of this polynomial, okay? When k is equal k plus 1. It's necessary because this remake said that if the k equal 1, I need only the Capelli type trace polynomial of the order 2. And the lemma brought this result. Okay. This is a main result of this talk, okay? We say that over a field of characteristic 0, the Jordan algebra, the Jordan algebra of matrix equated by the Jordan product have base. All trace identity of the Jordan algebra, when considered matrix equated by the Jordan product, follows from the Cayley-Hamilton polynomial of degree n and from the trace polynomial nk when k is equal n square minus 1. The similar result we have by this Jordan algebra, but we need to I need to careful because the dimensional of the Jordan algebra, okay? In this case, k, nk, this k is equal the dimension of the Jordan algebra minus 1, okay? Okay. To conclude my presentation, I will make final comments, okay? The first one, we improved the description for the embedded problem on the previous algebras. In other work, in 2018, we make it as some problem embed problem for this Jordan algebra, okay? But in this case, we consider only substitution by Cayley-Hamilton polynomial and Capelli polynomial nk. Just now. Here, in this work, we established the spectral property of the ideal of trace identity for this Jordan algebra as well. Okay? And Em resumo, we answered the question lifted by Shestakov in 1982, when considered the special Jordan algebras, special central simple Jordan algebras, over a field of characteristic 0. Okay? The third one, we obtain upper bound of the degrees of the tracing monomials modulo the T ideal formed by our trace identity for each Jordan algebra. It's important to study the geometry of these algebras, okay? And the last one, these results are extended for, I can extend to any central simple special Jordan algebra. Okay, this is my talk. Here the main reference, okay? And thank you. Thanks so much. Thank you for your attention.
Thank you. Thanks. Okay, are there comments or questions? Yes, okay. Okay, Artem.
Well, I have one question. Okay, so Claudemir, do you know what is a group of automorphism of some of these special Jordan algebras? What I'm asking, it will be in the second part of my question, okay? Well, probably it's not, but I never worked with Jordan algebra, so I don't really know much about it. So do you know what is a group of automorphism of special Jordan central algebras?
Can I answer in Portuguese, Professor Artem Lopatin, or in English? Because my English is not very good.
Well, you could answer in Portuguese, it's okay.
Ok. Eu não tenho certeza se eu entendi sua pergunta, mas acredito que você perguntou quais são os grupos de automorfismo, é isso?
Isso, exatamente.
Ok. O grupo de automorfismo das álgebras de Jordan nos casos de dimensão finita, né? Nos casos que eu trabalhei, são aquele grupo dos automorfismos, o grupo ortogonal, o grupo simplético e se eu não me engano, do Albert é o F4, né? Então, são álgebras de Lie, são grupos de Lie, né? Então, é bem conhecido esses grupos.
Tá bom, eu fui pensando justamente isso. Então, agora eu tenho a segunda parte da minha dúvida. Essa dúvida é a seguinte. Por exemplo, então, destes traços, tá? Acho que exatamente do tipo álgebra de invariantes, com relação da ação do grupo de... Sim, tá?
Não entendi, professor.
Então, acho que traços de álgebra de Jordan é exatamente uma álgebra de invariantes, com relação da ação de grupo de automorfismos. Tá bom, aqui nós podemos introduzir algumas definições adicionais, por mais ou menos. Então, e com relação a isso, eu tenho a dúvida seguinte. Então, sua descrição de identidades com traço, acho que implica de identidades que só contém traço, que não contém outras letras. Todas as letras são dentro de traços. É também ou não?
A primeira questão, né? No caso, nesses nossos, no caso especial, né, de ordem especial, você tem razão. Os traços puros, né, são conhecidos com o grupo o grupo das a álgebra das invariantes pelo grupo dos automorfismos. E aí, por considerar os traços não degenerados, aí você pode estudar apenas os traços, né, puros, mas só que para descrever as identidades você tem que utilizar a não degeneralidade para utilizar o fato do traço usual, como a gente definiu. Então, para esse caso específico, você tem razão. Isso daí não acontece para álgebras de Albert, por exemplo, e essa ideia de pegar os traços puros e jogar para os traços através da não degeneralidade do traço das álgebras de Jordan simples, não é tão assim imediato, né? Você precisa fazer alguns artifícios. No nosso caso aqui, a gente considerou colocar variáveis bem específicas em cada espaço, em cada slot no traço, para que quando a gente cancelasse, a gente conseguia retornar a álgebra de imediato, né? Uma álgebra que, aparentemente, eu não consegui fazer isso ainda, por exemplo, é a álgebra dos octônios, né? As álgebras dos octônios, existe uma teoria que diz quais são as relações entre as invariantes, né? Que é a de Kenny-Hamilton de grau 2, mas a gente, pelo menos por enquanto, eu ainda não consegui transcrever isso para o traço como a gente está definindo aqui, né? As identidades com traço, né? Que a gente não precisa necessariamente só ter traços, né? A gente pode ter monômios fora do traço, né? Só que o traço é comutativo, então a gente pode colocar o monômio para frente.
Uhum. Ah, tá bom. Então, tá bom. Obrigado pela sua resposta.
Thank you.
Plamen?
Okay, I want to recall only that this description of the automorphisms, the groups of automorphism of simple Jordan algebras, finite dimensional simple Jordan algebras, is very well known. You find it, in fact, in this famous Jacobson book, but it is not collected together. So you find somewhere in the first 20 pages, somewhere as an exercise, the automorphisms of the algebra of a bilinear form. And then later on, they appear, they pop up sometimes, but you can find there the description of the automorphism. So if you want to cite it somewhere, it is Jacobson book, but don't cite pages at all.
No, thank you.
Thank you, Clem.
Okay, thank you. Some more comments? Okay, let's thank Claudemir again. Thank you,
Thank you.
Claudemir.
Thank you.
Okay, we have 2 minutes left. See you later.